Welcome back. Our next speaker is Davoud Cheraghi from Imperial College London, and he's going to talk about satellite renormalisations and small divisors. All yours.
Is it okay? Yes. So during my childhood, when I was like, a quarter of my current age, so movies and TV series from India were very popular at the time, and it was kind of like a constant part of our lives. And the nice highlight of most of those movies were like group dance. So there was always a group dance at the end, which was like the most important part. So it feels very nice to be here. Thank you for the opportunity. And if you have a chance to see one of those group dances, I would highly recommend. I'm sorry to the experts that my talk is rather elementary. I prepared this when the conference looked a bit broader, but I was told by Roma that the complex dynamicists have taken over this. Yes, it's working. Yes. So the topic is about nonlinear dynamics. So nonlinear dynamics is where you have an analytic map, say from the real line to the real line, or from an open set in the complex plane to an open set in the complex plane. And the main goal usually is to explain the orbits of maps. Yes? So, dynamical system is a huge area. In this particular subject, there are some difficulties. So there are two main sources of difficulties. So one is the nonlinearity. As you iterate the map, these nonlinearities can combine and become more and more complicated. And the second issue is the non-invertibility of the map. Yeah. So if you have like a partial covering structure, or even if you have a nice covering structure, there's a combinatorial aspect that comes into play, and it becomes combined with the analytic aspect. And these things usually don't go very well together. Yeah? So we understand this from the time we start doing mathematics in undergrad. So a main central object here is the quadratic family. So in some ways, it is the easiest one. So in terms of nonlinearity, the derivative is a linear map. And in terms of the combinatorics, or the non-invertibility, is just a 2-to-1 covering map. Yes. So there are reasons why this is like central in the topic. So one simple answer is that for many maps, you could have a return to a region where the map is conjugate to a quadratic polynomial. Yeah, this happens very often, but there are other reasons that, if this is the simplest and we have difficulties understanding this, then we should actually spend more time on it. Yes. So the beginning of the theory is in the 80s or maybe late 70s, is for real parameter C. So this P sub C is conjugate to a member of what is known as the logistic family. So many non-trivial phenomena happens in that case. I'm not going to go through all of them. So this period doubling bifurcations, I guess everybody knows about these things. So despite the map being real, so the techniques that are used often are coming from complex analysis and geometry. This is surprising for some people. So since 1980s, there has been a lot of work on the complex parameters. And still, we don't quite understand all of them. And the purpose of this talk is to give you a glimpse into what are the difficulties, why are we, what are the challenges that we face. So no one has done this, so I'm going to do it. I don't know if it's useful. So the Julia set of a map is the part where the non-trivial dynamics happens. So nearby orbits are unstable. It's a compact subset of the plane, and outside the Julia set, the dynamics is trivial. Yeah? So we will, from now on, only talk about things happening on the Julia set. So, and here are two pictures. There are two possibilities. Either you have a totally disconnected set. It's a Cantor set on the right-hand side, or or a connected piece. These are the only two possibilities. And in general, there's a classification of quadratic maps in terms of their types. So the simplest case is the hyperbolic and the parabolic case. These have like an attracting or a parabolic cycle. And the next one is non-renormalizable. They are maps with almost Markov behavior. And then infinite renormalizable maps. These are where you have a case where the return has this local dynamics is somehow unrelated from what is happening at the global scale. Yeah? And this happens at many, many scales. Yeah? I will make this more precise in a moment. And the last case is the irrational indifferent case, where you have a periodic cycle where the derivative or the multiplier at the cycle is of the form e to the 2 pi I alpha for an irrational number alpha. Yeah? So your map is tangent to an irrational rotation. So these guys have so this classification is based on the dynamical behavior. So the hyperbolic case is the easiest, as I said. So the Julia set has measure 0. Almost every orbit will either tend to infinity or to the cycle. And pretty much everything is understood already in the 1910s. And the second case is non-renormalizable. So in here, there's a Yoko's puzzle piece technology that gives a symbolic description of the dynamics. So again, the Julia set has measure 0. These are some of the people who have contributed to the area. There's a notion of rigidity that is very important related to the structure of the Mandelbrot set and so on. And in case infinitely renormalizable, this is probably you remember the Feigenbaum map. This is a generalization of the Feigenbaum map. But this in general is more complicated. There are non-locally connected Julia sets. There are also locally connected Julia sets. There are examples with positive area and so on and so on. So the list of people who have worked on the topic is longer. But we still don't understand all of them. Yes? And the last case is the irrational indifferent case. So this is where you have Ziegel disks, Kramer fixed points, hedgehogs. And there are examples of positive area Julia sets. And that's like a list of people who have contributed to the area. So I put the list in this order because as you go from the top to the bottom, things get more difficult. And the reason for that is that the dynamics becomes more and more neutral. Okay? So we know that some form of expansion is very important in the description of nonlinear dynamics. And for the purpose of this talk, we are looking at the intertwining between the last two cases. Yeah, so the last two cases are very highly intertwined together so that one influences the other and the other way around. And all of these guys to come together in this moduli space. Yeah, so the Mandelbrot set is the set of parameters for all quadratics with of one of those four types. It has a very complicated structure, and that is reflected in the complicated dynamics that you see in the previous slide. An important problem here, quite interesting, is the local connectivity of the Mandelbrot set. And this implies that the easier ones, the hyperbolic guys, are dense among all quadratic maps. Yeah? So if you take one of those complicated case 3 or case 4 maps, you can approximate it by a hyperbolic one, which has a very simple dynamics. Yeah? Happy so far? No dance so far, yeah? So there's a dance going on, but we don't see it yet. So a remarkable feature of the Mandelbrot set is the appearance of these little copies inside the Mandelbrot set. So you see two copies. The right-hand side is rather easy. It's obvious it's a Mandelbrot set. And the one on the left is also a Mandelbrot set. But there's this point where the cusp is opened. So this copy is sitting here. And the reason behind this appearance of little copies in the Mandelbrot set is renormalisation. Okay? So I'll define what a renormalisation is. So you don't need to read what is written. It looks complicated, but I've drawn a picture. So P sub C is quadratic-like renormalizable if you can find a simply connected region like the green at the center, where the return map, as you iterate, you come back and you cover the whole green. Yeah? So you get the blue region. And you want the return map to be a 2-to-1 branched covering. Yeah? It's a very nice, it's the simplest that you could have for a return. Yes? So just like the quadratic map, which is doing a double cover, this is locally doing a double cover. And this double cover that you see is somehow independent of what you had at the large scale. So what happens here is that the orbit of the critical point, so the critical point is the cross at the center, will move around and come back to the green. So we are mapping the green to the blue, but the critical point must come back into the green. Yeah? So it's not allowed to escape to the blue. Yeah? And it will happen forever. So because of this, we have divided the post-critical set, which is the closure of the orbit of the critical point, into these clusters of n portions. And we are hoping to use this division to understand the post-critical set, because the post-critical set is the important object in holomorphic dynamics. Okay? So it's the measured theoretic attractor, and in general, if you understand the post-critical set, you understand many problems. So it's not obvious that you can have such a thing. Yeah? So for a given map, can we find a domain and then time n where this happens? So this was studied by Davoud and Hubbard in the classic work, where they say that this renormalization can happen, and anytime that you see one of them, it's one of the following two cases. It's either primitive type or satellite type. And the description is very easy. So primitive type is when this green and its iterates until you come back are disjoint. And the satellite is where you have completed the opposite. Yes? There's a fixed point on the green that you rotate around. You can never become disjoint because of this fixed. And you come back to where you started. Yeah, these are the only two possibilities. And each renormalization can be described by a combinatorial data. Yes? So the primitive on the left can be described by a tree known as the Hubbard tree. And you can also do it on the right-hand side, but the right-hand side is a tree that is much easier. So it's basically just one vertex with many edges coming out. And it's easier to describe that tree by a rational number. Yeah? So there's a rational number P over Q, where Q tells me how many edges I have. And P tells me that the first edge is mapped to which edge. You know, after you map it to the pth edge, because there's a map going on. And you can map, say, the first one to you can map this to the immediately next one, which will be like, say, 1 over 6 here. But there could be a situation where you map this to maybe to the third one, and then so on. So this number, it's easier for me to describe this by a rational number P over Q. And again, Davoud Hubbard say that every rational number, every non-zero rational number is realized. But we only care about these rational numbers modular integers, because if you rotate by a q plus 1 is the same as rotating by 1. So if you have one of these renormalizations and you understand the dynamics of the return map, then you completely understand the dynamics of the original map. Yes, so it's again part of the classic business here. So it would be nice if the return map is not renormalizable, but that's not, we are not lucky enough, or life is not easy enough. So the return map itself could be renormalizable. Yeah, so that's a situation where, so maybe on the right-hand side I have this picture, and I'll make it easier. So there are 3 pieces. So my return, P sub c to the 3, I forget about the rest, and I only look at the return map, which is like a double cover from here to over itself. I may have a renormalization structure here as well. So it could be, say, a domain here, which maps like this and like this, which is of type, say, 1 over 4 in this case. So that would be the second renormalization. Same story, if I understand the dynamics of that return, then I can go back and understand the dynamics of the global map. But it's possible that a map could have infinitely many such structures. So that means you can get a nest of domains, not necessarily shrinking, but a nest of domains that are around the critical point and larger return times where the return is a double cover. Yeah, that can happen. And in fact, if you give me any sequence of rational numbers, there is at least one map that realizes that combinatorics. Yes, so the uniqueness is not obvious. The uniqueness is related to the local connectivity of the Mandelbrot set I mentioned earlier. But we know that at least one exists. So the main question, of course, we face is how do we explain the dynamics of an infinitely renormalizable map? So there are two themes. So the primitive case, this has been successfully studied in the last 4 decades. So for many combinatorial types, we know that there is a pre-compactness of the renormalization. So that means the returns, so the return maps from this UNs to the VNs form a pre-compact class. And one has to be a bit careful because if these domains are shrinking to the critical point, what does pre-compactness mean? So you need to rescale maybe to a definite size and then talk about the pre-compactness. But this has been very successful. It has many consequences. I've listed some of them. So it immediately implies that the post-critical set is a Cantor set with bounded geometry. Bounded geometry means that the gaps that you have around these Cantor sets are definite. Yes. So another consequence is that P sub C is rigid. You have local connectivity at that parameter C. And there are there's remarkable examples of positive area as well. So they are not obvious consequences of the a priori bounds. In fact, as far as I know, it's still open whether a priori bounds would imply the second property that P sub C is rigid. Yes? So what we know is under some extra assumptions that this is true. So it just shows that the difficulty involved to deal with the problem. So when you go to the satellite case, we already know, or it was known very early on, that the pre-compactness cannot be true. Yes. In general, you cannot have pre-compactness. Or the domains where you do the renormalization don't necessarily shrink. Yes. So it's a situation where this domain, you go to the next one, it's also big. You have a return. Some of them will get small, but at least the one around the critical point is big. You go to the next one, it's still big. Yeah, and they don't necessarily shrink to a single point. So nevertheless, there has been some cases that have been understood. So the notable one is the Feigenbaum map, is when the combinatorics is 1/2, 1/2, 1/2. So we have a constant type 1/2. And C is real. So the symmetry is very important there. So there are non-locally connected Julia sets. There are examples of positive area, again, by Bouf-Sherita and Davoud-Kolyubich. So the example by Bouf-Sherita is a very Liouvillean type when the denominators QNs grow very fast. And the example by Davoud-Kolyubich is the opposite, when you have bounded type. So there's local connectivity of the Mandelbrot set by Levin, which is a different kind of a method that he uses, with the transversality and so on. And we have had a result on this with Mitso. And again, our result is for more on the Liouvillean type, when there's a growth condition. And the Davoud-Kolyubich is more in the bounded type regime. And the final result is what I have done on with my student on topology and geometry of the post-critical set. Yes. I will mostly focus on the last piece. So in fact, the aim is to tell you, a little bit about the complications that come in when you study this problem. So take a map P sub C, which is infinitely renormalizable of type Pi over Qi. We fix this. So I've drawn the first renormalization. So there's this fixed point there that we call the dividing fixed point. So there's this general Yoko's inequality that says that at the dividing fixed point, called the sigma 1, the derivative mu1 satisfies such an inequality. So mu1 must be between 1 and 1 plus big O of 1 over q1. So if I write the continued fraction expansion of p1 over q1, it has a finite continuous fraction, so it's a rational number. So if q1 is very large, I see in particular that mu1 is very close to 1. Yeah, it's pinched between these numbers. So q1 can be large for various reasons. One is that, say p1 over q1 is 1 over b11, so the continuous fraction is just very short. But q1 could be large because there is a very long continuous fraction, but the entries are just bounded. Yeah? So you could just have 1, 1, 1, 1, but still the q1 is large. But there are also other possibilities where you have one number in the entries that is very large, but all the other ones are small. Yes? So there's a two-dimensional aspect that will come into play in a moment. So if, in particular, if q1 is extremely large, yes, you should think of numbers that are have a continuous fraction that is like 10 million digits. Yes, when q1 is very large, you expect your dynamics, so the dynamics of that map, to be close to the dynamics of a map of that form, which has an irrationally indifferent fixed point, with the entries that we know the beginning of. Yeah? So the beginning of the entries are the same as the entries for P1 over Q1. So you have B11, B12 up to some B1M, and then I don't know the rest. Yes? We just know that they are close. So that's the first one. We go to the second renormalization. So there is the dividing fixed point sigma 2. So it's this one here. And again, I can see the Yoko's inequality that tells me that mu2 is now between 1 and 1 plus big O of q1 over q2. Okay? So this big O has a constant that is uniform, independent of the first inequality and the second inequality and the later ones. So similarly, you can say that if q2 is large, for whatever reason, the dynamics of some map with an irrational indifferent fixed point will influence the dynamics of what you see for the return map. Yeah, so at this point, this quadratic map has an irrational indifferent fixed point, And again, you can look at its digits. I didn't write it. So for this alpha 2, the entries, you look at the beginning, will be the same as the one for P2 over Q2. Yes, are you following? Happy? Yes. So you can repeat this, yes? So you can go to the nth renormalization, and the inequality will tell me that mu n is between 1 and 1 plus big O of Q1, Q2 to Qn minus 1 over Qn. Yeah? And the outcome of this discussion is that the dynamics of this P sub C is influenced by infinitely many irrationally indifferent fixed points, which are independent from each other. Yes, because P1 over Pi over Qis are independent. So that means the corresponding numbers alpha n's are independent. And all these independent guys are influencing your single map. So if you hope to take this approach to explain the dynamics of your starting map, you need to deal with two problems. One is that this estimate is not very good. So if you want to rely on such an estimate, you need to impose an extremely aggressive growth condition on Qn. Yes? So it depends on the history of your combinatorics. And the second thing is that you need to understand the dynamics of irrational in different maps, but not in an individual fashion, but in fact you need some uniform estimates over all of them and how they change from one to the other. Yes? So I'm going to, in the next 2 slides, I'm going to answer these 2 questions. And then I say how they combine to give an answer to the infinitely renormalizable map. Okay? So first look at the estimate on the multipliers. So this is the result we had with Mitso in 2015. It's part of our paper on the hyperbolicity of the satellite renormalization. So this statement is not written there, but it's there. At that point, I didn't realize how significant it was. So it says that so there is a big N, it's a number, say 100, or we don't know what it is, it's a large number, that if you take any sequence of rational numbers, pi over qi, with the entries are at least n, we have the following 2 properties. The first one is that there exists a parameter c of tau. So tau is my sequence, pi over qi. There's this complex parameter c of tau, such that p sub c of tau is infinitely satellite renormalizable of type tau. Okay? So it has these structures with pi over qi. And the multiplier is between 1 and 1 plus big O of 1 over qn square. Okay? So it became independent from the history. And also the 1 over qn became 1 over qn square. Yes? So in fact, what we have is a much stronger estimate. We know the location of the multiplier, not just that it is pinched between 1 and that number. It's a more precise statement, but it will get complicated. I'll keep it simple here, so because we're not going to go into too much detail. So at the moment, we know that this parameter c of tau exists. Yes. If I impose a bit more growth condition, we know that this c of tau is actually unique. So if the entries are growing in a quadratic fashion, so in fact they only need to grow eventually in a quadratic fashion, each entry is more than the double of the previous one, square of the previous one, then you have the uniqueness, and in particular m is locally connected at that parameter. Yeah. So the item 2 is not the purpose of the main stream of the talk, so I don't spend too much time on this. So we compare this estimating 1 with the one coming from the Yoko's inequality, and you see there's a huge gap. So that was the first ingredient. So the second ingredient is the statement that I guess many of you have seen. So it says if you have an irrational indifferent fixed point under the same condition, if the entries are at least n, then the post-critical set of that map will satisfy one of the following 3 cases. Yes, the post-critical set is either a Jordan curve, or a one-sided hairy Jordan curve, or a Cantor-Bouquet.
So what is your notation? P alpha is the
closure of the orbit of the critical point. Yes. So all these 3 cases, we know exactly under what number theoretic condition happens. So it's a topological statement, but behind the scene, there is a very precise geometric statement that says, precisely in terms of your arithmetic, if you know the digits up to here, then I understand the post-critical set up to this much of geometry. Okay. So I'm not going to give a precise definition of what these number theoretic conditions are, but they cover all cases. So I'm just going to say a little bit about the topology, because it will come important later. So a Jordan curve, we know what it is. So you take that Jordan curve, and the one-sided hairy Jordan curve is basically a Jordan curve with Jordan arcs coming out only on one side, but you have many of them. So there are uncountably many arcs coming out, so it's a scary object, as Mitsu mentioned. With the property that any of the arcs is accumulated from both sides by arcs. So anytime you see an arc, there is a sequence of arcs coming from both sides, converging to the point. Huh? Not the same size. So in the Hausdorff limit, you get the corresponding arc here. So we don't know if the lengths, we don't know, they're not. Yes, sorry.
But there are no naked pieces of arcs. I mean, all the time they're sort of stated by label, this is what you're saying.
Yes, exactly. So anytime I pick an arc, so in the Hausdorff topology, there's a sequence of arcs converging to it. But I mean, there are these extra conditions that you don't have arcs like this converging. Yeah, so this is like called a smoothness. But anyway, so I'm not going to be too precise here. So what I want to say is to explain a little bit how that comes up. Yes? So there, the fixed point at 0 is inside, and the region within the Jordan arc is invariant. So that's your Ziegel disk. So the map is conjugate to a rotation by an analytic map. So the critical point is an end point of one of the arcs. So the closure of this point will become the whole hairy Jordan curve. But the orbit of that point will never come back to that arc. Yes? So this arc is only obtained in the limit of the orbit. Yes? So that means there will be returns coming closer and closer until you form that set. So you wonder how this object is obtained, or how do you get such a guy? So the way it works is that you have the fixed point and you have the critical point somewhere here, say. So there's a rotational element. So you rotate around the point, and with the nonlinearity, you move close in and out. Okay? So you will move this action, make these actions simultaneously. So at the beginning, you just see a rotation. So it comes maybe here, 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 and then somewhere close to this. So when you have the return, I forget about the rest. I'm going to draw only under the return what the orbit is from here up to there. So what you will see is that there is so imagine an arc coming in close to 0 and then going out, and you get a number of points on that arc. And then it will repeat here, repeat here, repeat here, repeat under the return. And then I want to draw for you the next stage. So you take any pair of points you like, say, let's say these two. You can imagine an arc coming in close to 0 and then going out. Over that arc, you will have an orbit, but now the distances are shorter, and they go in and come out. Yes? And then you repeat this everywhere. So you keep repeating this. In the limit, you get the arc coming in from here to the fixed point. So that's this case. Yes? Yes, exactly. So it's really so the possibility that you have is that it depends on the arithmetic. So if you did move in and out, but the amount that you move in is not too much, you will form a Jordan curve. Yes. So the amount that you move in requires bigger and bigger digits. Yes. So for example, so how much I have moved inside here depends on your A2. And when I take the next pair, and how much I have moved in here will depend on A3, and so on. Yes. So if the AIs are, if you have moved in by some eta here, and in the next stage you want to move by the same amount eta, you need a much bigger number. Yes. So you will need bigger and bigger numbers to exert the same amount of, distorting behavior. So anyway, if the orbit stays like that, then you're in the Jordan curve. If you have enough force to go up to a certain distance, you get these arcs, but then there's a Jordan curve inside here. And if you have enough force, if the entries are getting extremely fast, growing extremely fast, you have enough to touch 0 in the limit. Questions? Happy? Yes?
Do you know the regularity of case 1? How can it be?
It's a very good question. It was in my thesis to prove that this postcard has measure 0, and the most difficult case to deal with was case 1. Yes, so it can be quite bad. I don't want to make any statement at the moment, but I don't know about that. So a nice question is, for example, whether the dimension can be 2. Yes. Yeah. So the easiest case to deal with was case 3. So I have 20 minutes, so I need to move on. So combining this result and the earlier estimate, we get this dichotomy of the post-critical set for the infinitely satellite renormalizations. So if you take a sequence of rational numbers under the same condition, the entries are at least n. One of the following 2 cases happen. So there's an arithmetic condition that says tau satisfies a Hermann-Yocos-like arithmetic condition, and the post-critical set is a Cantor set of points. Or it does not satisfy that condition, and the P sub C is a hairy Cantor set. Yes, I'll say in a moment what that is. So this Hermann-Yocos condition is coming from this Bruno minus Hermann. Yeah. So that case kind of disappears when you move from the irrational indifferent to the infinitely renormalizable. That case disappears. Maybe I have time to explain this, and then you only inherit limits from those 2 cases. So what am I saying next? So it's a corollary that if you are in case 2, then the domains of renormalizations, the UIs, cannot shrink to the critical point. Yes? And I believe this is optimal, but I don't know the opposite. So in fact, there is a more precise statement that says if you take these fundamental domains, you remove the post-critical set, and you have these annuli in the complement of the post-critical set, we know precisely what is the modulus of that annulus. Up to a constant, we know the modulus of the annulus or the length of the hyperbolic geodesic that sits in there. It doesn't depend on the history, the combinatorics of the map. It only depends on the combinatorics on that level. It somehow shows independence of the geometry of these scales. So 2 comments. One is on the Hermann-Yocos-like condition. Yes?
On the previous slide, is there still evidence that the Mandelbrot set is connected is locally connected to this parameter?
Yes, so the statement that I mentioned earlier in the joint work with Shishikura applies to those cases. Yeah, so in those cases, we do know there. Yes. So not for all of them, but for most of them. Yes. So for the uniqueness, I needed a growth condition. But somehow, you can have a number that doesn't quite have a growth condition occasionally, but it still satisfies this. Yes? Maybe I'll make a comment in a moment. Yeah. So the Hermann-Yocos-like condition that we obtained here is in the spirit of the Hermann-Yocos optimal condition that comes up in the problem of the linearization of analytic circle maps. Yes? When you study the analytic circle maps, you can ask when the map is analytically conjugate to a rotation, and there's an optimal condition for this obtained by Yocos. It's quite complicated, so I wouldn't go into defining this. But the condition that we obtain is kind of similar to that, but it's a two-dimensional version of that. Because in the Hermann-Jacob case, you have one irrational number, and the condition is on that. But here you have a sequence of rational numbers, and you impose this condition on them. And there is this transition from one rational to the next rational. This step is like a dimension. Yeah? So it's a dimension because, I don't know if I can explain this. So maybe I make the simpler comments and then I try. So if the entries, so there are three examples. If the entries in all of the pi over qi's are uniformly bounded, yeah, so the entries are bij's, and then the sequence will be Hermann-Jacob-like. If the first entry from each number is uniformly bounded, then the number will be still Hermann-Jacob-like. So if not the first entry, so it could be that these numbers pi over qi's have like maybe finite, maybe have a continued fraction of length 1, then the next one has length 5, length 3, 9, and so on. But if it happens that eventually they all have lengths at least 5 and so on, and if the fifth entry for all of them uniformly bounded, you still get a Hermann-Jacob-like. This is a bit different from the nature of the Hermann-Jacob numbers for irrational numbers. But I don't think I have set up enough to explain this, but maybe it's not even necessary. And the last case.
Do you have a definition on your slides or no?
No, I don't. Yes. No. So if you know the Hermann condition, do you know the Hermann condition, the Hermann-Jacob? So there is the Hermann-Jacob condition. The Hermann-Jacob condition has a model map that you iterate the model map and you say whether the sequence behaves in a certain way or not, and then that causes a division. Okay. So here also, for each pi over qi, you take the same model map by Hermann, but then there's a transition from one rational number to the next rational number, for which we have a new model. So you repeat applying two maps. And then you ask whether a certain thing happens or not. Yeah? So Jacob gave like maybe 3 different definitions of the Hermann-Jacob condition. So some of them are more group theoretic. But we didn't spend enough time to find alternative presentations of the same condition. So we just have one condition and we know it's optimal. And the second comment is about the Hairy-Cantor sets. I'm not going to spend too much time on that. I don't give a precise definition because there's a written version of this already. So a Hairy-Cantor set is an object in the plane such that each component is either a single point or an arc. And the important property is that each arc is approximated from both sides by arcs. Yeah, it's similar to that, but you don't have this Jordan curve part. Yes, so there are 5 axioms that if any set that satisfies those 5 axioms is a hairy Jordan curve. So my last slide is on the ingredients of the proof of the dichotomy. So the main ingredient that probably most of you know is the near parabolic renormalization of Inao and Shishikura. It was introduced in 2003 or 2006. It's an important part of this. And the second one is the result I already mentioned. It's the optimal estimate on the multipliers of the dividing fixed points. The third ingredient is a toy model for the satellite renormalizations. Yeah, this was done with my former PhD student, Pedro Amfar. So in fact, what we did at the time was to build a toy model for the post-critical set. and the map on the post-critical set. But at some point I realized, after writing 80 pages, I realized that it is better to build a toy model for the whole renormalization. Yes, because of future applications, and also things are more civilized. So I have this burden of rewriting this toy model, this 80 pages toy model in a different way. And part of the problem is that Pedramfar has decided that mathematics is too slow for him. So writing a long paper and also verifying it, so he thought that by the time this can be written, he can develop an algorithm that would verify proofs. So he moved to the area of formal proof verifications. And he thinks very soon he will write programs that produce, that can guess and prove, new theorems. So he has moved to Purdue University. I was quite surprised that he could make a transition in such a short period of time. So he works there on that topic. And the final thing is there is a rigidity result that I had developed a bit earlier. So it's a statement that says if you have two renormalization schemes with roughly similar geometric properties, then the two renormalizations must be conjugate. Yeah? It is a stronger property than just saying that if I have a toy model for one map and I have an actual another map, they are conjugate. It would imply that, but it would give even more. So I put the dates 2018, but that was the time I was convinced we can give a proof. But it has it has been going on, so that's why there is a dash at the end. But I'm pretty sure we can have a proof. It's mostly written, but it's still going on. Yeah, so you can count it as a work in progress. So thank you for your attention.